So the title of my talk would be like classical quantum hybrid algorithms for optimization and differential equation solving. So to give a brief introduction about myself, I am from Karnataka and I did my BSc in physics, chemistry and mathematics from Urajas College, Mysore. And following that, I did masters from Central University of Karnataka in Gulbarga. And then I did PhD. I think Indra already mentioned that I did PhD from University of Naples, and then 1 year postdoc, and then I did another postdoc at KTH where I was in computer science department in HPC group. And in May 2025, I completed that postdoc position. So my talk will have two parts. The first part essentially was what I did during my PhD, which is about quantum annealing and using classical algorithms such as genetic algorithms for problems such as shortcuts to diabeticity and annealing schedule optimization. And I also used a bit of deep learning to optimize or predict the optimal annealing schedules. So this part of the talk is like how classical algorithms such as genetic algorithms and deep learning can assist quantum computing. So the second part of the talk is focused on classical quantum hybrid neural networks, and with some experimental demonstration, I was able to show that the presence of quantum can assist like classical algorithms such as neural networks and so on. And I will show an example in plasma physics of this application of classical quantum hybrid neural network. So the first part of the talk is, which is about quantum annealing, is based on these two research articles, and I did this work in University of Naples, Federico II. So quantum computing, you might be like the most popular kind of quantum computing is this gate model quantum computing. So where you use like discrete quantum operations, you start the quantum system in a particular state, and you implement different unitaries or quantum gates, and then you measure certain like expectation for value. For example, in this setup, there are many quantum algorithms that are designed. And to broadly tell what quantum computing is, that it's a kind of computing where you use quantum effects which can hopefully enhance the performance in terms of speed up or accuracy or some kind of advantage that it can bring. And so in gate model quantum computing, there is of course quantum superposition, quantum entanglement, this kind of phenomena come into play. And in this is adiabatic quantum computing, which is based on the adiabatic theorem of quantum mechanics, and it is majorly used in solving optimization problems in practical sense. For example, D-Wave, which is a quantum annealer actually, and that is a company that is predominantly using this quantum kind of quantum computing. And while for gate model, there are many popular companies which are invested in or interested in this kind of quantum computing.
So what is the difference between annealing and adiabatic?
So I can.
Bit on the later side.
Yeah. I mean, so adiabatic quantum computing is based. It's a theoretical model. So it's based on the adiabatic theorem of quantum mechanics, which means that if you prepare a system in the eigenstate of a time-dependent Hamiltonian, and if you evolve it slowly enough, it continues to be in that particular eigenstate throughout the evolution. And how slow should this evolution be so that it always stays in the ground state is given by this adiabatic time scale. As you can see, this adiabatic time scale is inversely proportional to the energy gap in the instantaneous eigen spectrum, like the minimum energy gap. So this becomes important later in the talk. Well, what
So you said instantaneous energy gap, instantaneous as opposed to what kind of energy gap? Like average energy gap.
no, if you solve the uh, like if you diagonalize the Hamiltonian at every instant of this evolution, the energy spectrum that you get. In that, for example, if we start in the
No,
ground,
I understand what you mean. I'm just asking instantaneous as opposed to what?
So
what kind of other gaps? Well, right.
So what other kind of gap do you have in mind? Instantaneous is like at
Like
every
Yeah.
the spaces for average energy.
Oh,
Yes, inversely proportional to average energy.
or you can take the minimum of all gaps. I see.
Yeah.
But this statement of the adiabatic time scale is not rigorous. This is used
Yes.
a lot. This is not rigorous.
yes, I think it's one of the earliest and most used
Right.
time scale, and there are many, I think, recent or and rigorous
No, but
time
say,
scales.
why is it not rigorous?
Because it's not equal. Like you can show that this is like the leading order term. There are other terms which contribute, and depending on
Yes, so it's an approximate. So it's actually greater than this.
yeah, greater equal.
Yeah,
Oh, I see.
yeah, I think it's like the minimum time that you have to evolve it for. And like in most of my work, I have considered this adiabatic time scale, and I take this as the time that you need to do so that you are sure that it will be in the ground state. And to briefly discuss the kind of problems is, for example, combinatorial optimization problems. An example is the traveling salesman problem. You can map this kind of problem like a traveling salesman has to traverse these many cities and in the lowest time or distance possible. So which is the best path, and this kind of problem can be rewritten as a Ising Hamiltonian of this form. For example, the distance between the two cities is mapped in this coupling term between the two spins. Like you can, if it is a spin system, and similarly, this kind of weight of if it travels to the in the ith step, if you go into the particular city and so on, this kind of mapping exists. And so, what we want is that we want the system to be in the ground state. If we find the ground state of this Hamiltonian, we'll find the optimal solution to this problem. So, what in adiabatic quantum computing, the main principle is that you begin in the easy to prepare ground state and you slowly evolve the interactions between the system so that at the final time the Hamiltonian corresponds to this problem and the ground state, and because of the adiabatic evolution we are still in the ground state of that system evolution. We'll find the solution to this problem. That is the main idea. And quantum annealing is a kind of is for example, it is a kind of similar idea, adiabatic quantum. It is also an adiabatic quantum computing, but it doesn't strictly have to be adiabatic, which means that it doesn't have to be in the ground, the system doesn't have to be in the ground state at all the times. Sometimes in this technique, you can engineer this dynamic such that it can transition to the excited states and comes back to the ground state again. And at the final time, you are at the ground state.
So in the previous slides, so you can prepare ground state of the new Hamiltonian, whatever Hamiltonian is the target Hamiltonian. But how do I know that I will reach all kind of Hamiltonian? So what kind of problems can be implemented through annealing?
So
Adiabatic or annealing?
yeah,
Annealers are adiabatic.
yeah. So usually the target is this kind of Ising Hamiltonian.
So for example, if I have this Hamiltonian, then the target Hamiltonian will almost look like this
Yes.
with certain other parameters.
Yeah.
So it still will be some eigen instead of the Ising Hamiltonian.
Yes.
So you cannot go from Ising to say something else, for example, Hubbard model or something. You cannot go from.
In principle, in adiabatic quantum computing, you can do like actually in the preparation state, you are in a simple like a superposition state. So the Hamiltonian simple sigma x in the Hamiltonian. This should be the final Hamiltonian if the problem. So I mean mathematically you can start from this Hamiltonian and go to other Hamiltonian and so on.
I'm worried about the forms. So I will have at most at the end of the day I will be having some general Ising chain.
No, it's any Hamiltonian Hamiltonian. Why?
No, so that will depend on what I have in the beginning. So I'm just tuning the parameter of the Hamiltonian.
Yeah, so what happens is that you have an initial Hamiltonian, you have a final Hamiltonian.
You have to have a path.
Yeah, so basically, as long as you have a path, so
So I am worried that it will, and if I want to achieve some, go to some general Hamiltonian, I cannot from arbitrary initial point.
I guess as long as you can parameterize in a way that
So
the one is trivial, then
this is why these rigorous statements are important. They define what kind of Hamiltonians you want, an initial Hamiltonian, what kind of what conditions you need on the norm so that an adiabatic path exists.
Exactly. So that makes much more meaningful that you will have set of input, set of output, but not arbitrary.
Yeah, as long as the time evolution is slow, you will not be able to cross curves. And when you don't cross curves, you are always going to fall down into a valley which is more optimal.
Yeah,
Rather
that
than
is
crossing.
the principle. That is fine. I am asking that what kind of Hamiltonians you can tune from hot Hamiltonians.
So can you go from any initial to any final Hamilton? There has to be a path.
Yeah.
From the downstate of the initial Hamilton to the ground state.
So wherever you are able to control your parameters in such a way so that one set of parameters is lowered in their value and the other set of parameters they keep increasing in. So you go on. So it's like, let's say superposition of the state one and state two, and the coefficient for state one will keep getting lower, coefficient for state two will keep getting higher. So the evolution has to be managed that way. So I'm just curious, what does slow time evolution mean here? I mean, this is probably more a hardware related issue. I mean, how do you know that an evolution is slow or fast?
it's relative to the energy gap. Well, that's what she's
No, but energy gap, given any energy gap, you can still have a fast evolution or a slow evolution, right?
It has to be in that order of time.
Yeah.
No, but how do you do that? That's what I'm trying to understand.
So
How do-
this is kind of question.
It's a hardware question, right?
Yeah, I mean, there is a priori no way. If I give you general, say, initial Hamilton, final Hamilton, you need to construct what is called an adiabatic schedule, right? Which will determine how fast you will go.
No, the schedule is theoretically determined. But how do you ensure that it will actually follow this?
Oh, because the schedule is saying at what rate you're changing your parameters, I don't know which is a control of your
I got it, but I'm saying, how do you actually physically ensure that you
So are you thinking of that soft kind of setting where you don't know if the machine is quantumly working or not? Where theoretically you do have a
I think it depends on the system and the control time scales.
Yeah, you're assuming like somehow you have like say a magnet or something, right? You have state only signal from me.
the application of any kind of field could be like magnetic or whatever, like it has to be controlled in time scale.
Yeah, that's what I'm saying. Like the magnetic field, you have a computer, you're saying that you want to take it from 0.5 Tesla to 0.6 Tesla in this time, and then you depending on the schedule, you calculate it.
Because you start from local sigma x's, and then you end up with to something which is local sigma z. So basically, you have to just tune like a magnetic field.
But that process needs to be done using an external field.
Yeah.
Right. So as Atul is saying, that external field application has to be scheduled in time.
Yeah. And you just follow whatever you
and this is all contingent upon the fact that the machine works. And it works.
You're assuming that the mathematical modeling that you have is actually describing physical reality. This is an assumption. It's not a device. Please carry on.
Yeah. So as I was saying that in quantum annealing, it doesn't have to be strictly adiabatic in the sense it doesn't have to follow the ground state path always. So and it is this process is also inspired from this already existing numerical technique of simulated annealing, where they use this temperature parameters to jump across this energy barriers. And in quantum annealing, supposedly this going from one minima to other minima can happen through tunneling. So this is one of the reasons that it is like a quantum process, because there is like the involvement of quantum phenomena of tunneling. And both adiabatic quantum computing and quantum annealing is usually constructed through this kind of Hamiltonian.
Could you describe what you have plotted on the graph? Is it like time on the x-axis and energy on the y, or is it some
Energy. On the, yeah,
the y-axis is energy?
yeah. Yes, the y-axis is energy,
Okay.
and this
X-axis is time.
time. Yeah, it's not.
So it's tunneling in time, you're saying.
Yeah, Exactly.
I mean, it's not just time. It's any parameter which can be mapped to a differential
Yeah.
process.
Yeah, so in adiabatic quantum computing, for example, if we start with the superposition of all state, the energy landscape looks somewhat like a superposition of all states. And with time, this energy barrier itself is more slowly into other structures. And at the final time, we are in the the energy structure corresponds to our problem Hamiltonian. And the system is always in the ground state.
So that's just adiabatic, right? If the state
Yeah.
in the ground state, it's adiabatic. But here you're saying some
Yeah. In quantum annealing, what can happen is given this energy structure, the system doesn't have to be in the ground state always. It can tunnel to other states.
So you have to go faster than the adiabatic time.
Yeah, you can go faster than the adiabatic time
What do
scale.
you mean? You have to, if you don't, then you stay in the ground state.
Yeah, but that is the ideal case scenario that we want to be in the ground state. It will always be in the ground state in adiabatic.
So that's a theorem. What do you like? Is that not a theorem or some?
No.
Yeah, it is the theorem. So as long as we are following adiabatic theorem, we are sure to get the solution. But then, as I have shown you that the energy gap, the adiabatic time scale can blow up for difficult problems, which I will come to later. So we cannot afford to wait so long. If the energy,
Go faster.
yeah, if the energy gap is very slow in case of anti-hard problems, which is the case, then the adiabatic time scale is infinite. So it's not practical.
Okay, so that's what I was asking. That you have
Yeah.
to go faster than the adiabatic time scale.
Yeah, yes.
For this route.
Yes, exactly.
Also, it's very difficult to cool your system down completely so that it remains in the ground state. So in practice, you run these annealers, you're always at a slightly more energetic state. So there will be transitions like these, like thermal transitions
Yes.
with some small probability. Some of it might tunnel. So this is the thing. Now it becomes very heuristic at this stage. So some portion of your state might have some overlap with the ground state. Some of it may tunnel through. Some of it may go to the higher excited states. A lot of these things happen.
Yeah.
You're saying it's primarily temperature that is messing things up. So therefore you have to consider these.
Yes, so temperature does play a role.
Yeah. I think there are also.
I mean, even in closed quantum systems, here is applicable. So there, temperature will not have any role. But if you are in a real world kind of situation where your initial state is somehow you are able to prepare two thermal flows for something, then already it is not consistent.
So
Yeah.
you were saying something.
Yeah, and I mean there are also speculations that in D wave, so it's not clear if quantum tunneling is always the reason why this energy we are reaching the ground state. There could be like thermal fluctuations. There are thermal assisted tunneling. I'm not so expert or I don't understand that term, but temperature can lead to like it can be like cooling down the system and it's going to the ground state as well.
So how do you do theory for these kinds of things? Or is it just heuristics? Annealing?
Yeah, so this process is sorry, driven by this Hamiltonian. So which is like you start from a like
Yeah.
the system is
Hamiltonian.
described by the easy Hamiltonian, and you decrease this contribution slowly, and then you increase the problem contribution slowly. These are for the A and B are the annealing schedules. So this is how the this problem is studied. Like how, for example, how slowly we can do these things so that we reach the adiabatic. I mean,
But it's not adiabatic. That's my problem. Adiabatic, I understand. But here you're saying some simulated
Yeah.
thing is happening. So how do you model all this? Because in adiabatic, you're just taking the overlap with the ground states. It makes sense, right? Am I saying something wrong? No, stop me okay, because I don't know. So for the simulated annealing, you have like expressions for where you're checking tunneling happening as a function of thing, or how do you? Maybe it'll come later. Okay. Time.
I think it would have been helpful if one defines what is annealing
Yeah,
and what is the adiabatic computing.
I think the
Both are related very much
So
possible.
both are for most theoretical studies. This is the Hamiltonian for both.
that's fine.
Yes.
So
So
let's
this
carry on. We'll see. We'll understand.
this capital T is what if it is adiabatic time scale. For example, this parameterization of A of S, if we take a simplest choice, which is S is T of T, and A of S is 1 minus and S, this kind of thing. And this T, capital T, is determined by the adiabatic time scale, the final time for how long you have to do. Then this corresponds to the adiabatic quantum computation. And yeah, but then we will see that we will try this method with capital T naught much lesser than the adiabatic time scale, and we can change the paths of this.
What do you mean we will try? Like, is it a simulation, numerical simulation?
Yes.
Yeah, that's
Yes,
what I'm
we evolve this system. Like for example, I will show later that we change this A of S and B of S and or add additional terms.
And then you can check if it's solving. Like,
Yes,
that.
yes, exactly.
I thought like you're actually solving equations and stuff. That's why I was a bit concerned about what.
No, yeah.
And all the critical thing is lost if I define this Hamilton, where I will not be able to have a system that will follow this kind of interaction.
Okay.
This is a theoretical thing where I can write any Hamiltonian, right here.
Yes.
And with this Hamiltonian, I can reach from any to any. Where it's 0, I can pick any addition operator, and it's problem, I can pick any. But there is no guarantee that there will be a physical system that will follow that
Exactly.
Hamiltonian.
So most of the, for example, D wave, it only has, we can implement like 2 body interactions. That's why most of the times the QBO problems is what they call quadratic binary optimization problem, which looks like Ising Hamiltonian. That's usually the problem of interest.
They instantiate them with specialized forms and then.
Yeah, only so much interaction is available in physical systems.
Okay, thank you. Sorry for all the questions.
No problem. It's useful. Yeah. So coming back to this adiabatic time scale, this, as I said, this is one of the time scales. I'm considering it for now. And this adiabatic time scale is inversely proportional to the energy square. And for many hard problems, this gap is very small. And so the time scale can be very large and infinite as well. And it can lead to like the system transition into higher energy state. And at the final time, we are not in the ground state and we won't get the solution to this problem. So one of the ways this problem is tackled is through this techniques called shortcuts to adiabaticity. So which means like literally means you are not following the adiabatic time scale path, but you are finding some kind of shortcuts. So it's based on this idea, like if a waiter has to carry a glass of water from point A to B, then if he moves, he has to move very slowly so that if we don't, he doesn't spill it. But then, so he can tilt his tray a little bit so that he reaches fast and without spilling. It's a so this tilting is kind of an action or a alternate path so that the task is performed in a similar way. So in addition to this driving Hamiltonian, we add an additional counter-diabatic term so that it changes the path of the evolution or kind of avoids this energy crossings. So and this is kept 0 at initial and final time, so it doesn't change the final Hamiltonian. So we are still in the ground state of our required problem Hamiltonian. So this is the counter-diabatic operator that we can add. So and the analytical solution to what this counter-diabatic term should be is given, but this analytical solution also again depends, inversely depends on the energy terms, and we need to know the instantaneous, like the energy spectrum, like we need to diagonalize every time, but that is the part of our problem actually. Yeah, so yeah, exactly. So it's not a very useful approach. So there are variational methods to find this counter-diabatic operators.
So before you answer this counter-diabatic operator in the previous slide, is it locally Hamiltonian as well? Or?
This is like
no, these are just eigenterms, right? They don't have to be local.
yeah, these are not actually local.
So then there's no obvious way of implementing.
What is capital H here?
It's your initial Hamiltonian? No,
Total Hamiltonian.
Total Hamiltonian.
Total meaning like H0 plus H target.
Yeah.
Half schedule wages. Right?
Yeah.
In the middle.
In the middle. Oh, in the middle. Yeah.
So this is highly interacting, it seems.
Yeah.
So that is very irrelevant, right? Like even if you could, for instance, find the spectrum, right? And it's okay. The whole quality solves the problem, but
Yeah.
even then, it's not clear how you would physically implement.
Yeah. Exactly.
Physical implementation is far, far away.
Thanks. But mathematically, also these things are just it doesn't help. But okay, that's good.
Yeah. So this is the variational approach.
Sorry about that. I'm just trying to move the stupid thing on the top. Right. Oh, sorry about that.
So this in this paper they show this theory of how this transitions, the diabetic transitions that can happen can be modeled with this kind of term, and this is the a lambda not a lambda. This lambda is like the annealing schedule. Translate this problem to the previous conventions I showed. So we kind of have to add this term back so that the diabetic transitions are suppressed during the evolution. And so this is the they show that this finding this a lambda is equivalent to minimizing this function.
What is a diabetic transition? Like stuff that's not supposed to happen in an adiabatic transition.
Yeah, so when the
What
energy
exactly?
crossings, it goes to the higher energy state, that is, I think, termed as diabetic transitions. So, so this term is calculated like there are many ansatz that you can propose. There are this nested commutator ansatz. I think this is also not local, and there are this cyclic ansatz.
Like theory of comparison.
No, thank you.
Thank you. Wait, so I got a bit lost. So what do you mean by the transition can be modeled as a Hamiltonian? I'm a bit confused.
So this is the they say that these transitions that happen can be showed in the moving frame of reference, where this term is responsible for the the
transition can be shown to model and movement reference, which is I'm not following that sentence. What transition is not a mathematical word, is it?
I think the overall picture is like you want to maximize the gap between energy levels.
Yeah.
And if you add extra term, so they will come out expanding the gap.
No, but now she's talking about the diabetic transition, modeling of the transition itself. I don't know what that word means. Like, what does it mean to model a transition? What am I missing? Did you understand something? No,
I think it's an in between thing. So effective Hamiltonian should be such that it is expanding the gap, that is like transition. So the transition.
the thing of the energy gap.
Hamiltonian where there is no transition, kind of like if there is a this is the Hamiltonian which is showing now the transition. I think it's like written in a separate form.
Wait, so H0 was the easy Hamiltonian, yes?
Yeah.
And now, but
So in this case, sorry, the H0 is the total Hamiltonian used for driving the quantum annealing.
So this is like initial versus final. Oh, okay.
Yeah.
this is the full Hamiltonian, and now
Yeah.
you're adding an extra term to this, and you're calling it H effective.
Yeah. Yes.
And H effective has what property? That the energy gaps are very high, so there's no crossing. Is
Yeah,
that-
that I was guessing stability.
Yeah.
What is that? Can you
So-
tell?
So, to be honest, I don't remember the intricacies of this, but the main point is that we consider an ansatz of, for example, this is one of the ansatz that we need to add to this, and it is like variationally computed, like the final ground state probability is higher.
The ground state probability is higher. You mean like when you do the full evolution, you get a higher.
Yeah, exactly. In the final evolution.
So, okay, I ask you. So you turn on an interaction, you turn it off.
Yeah.
These are your terms in the middle. Right? Now you're trying to model what happens when you add these counter adiabatic
Yes.
driving terms.
Yes.
Right? That's what you're trying to do.
Yes.
But there is no way by which you can guarantee that the gaps are going to increase, right?
The gaps need not increase, but it maybe there is like in a similar gaps, but if you compute the path of the whole thing, there is no transition as such.
And that is what Anu's problem, like the word transition that I have also not getting.
Transition means from the ground to the higher excited state.
Yes.
But you are looking at diabetic transitions, which precisely means that you're looking at those transitions. Right?
Yeah. And then
And you are trying to gauge them away. I don't know what is happening.
If she doesn't remember the details, it's fine. Like, so we understand the basic idea that you're trying to minimize the, I guess, the gap.
No, maximize the gap, so
So let's increase the gap basically.
So minimize the transitions.
Is that
yes,
roughly
exactly.
correct?
Yes.
Okay. And then doing it variationally, so I'm guessing like they're adding these terms and checking if it succeeds, and then using that to figure out what Hamiltonian to use. I guess is
Yeah.
that perfect?
Yeah, exactly. So then they have to be like physically implementable terms with the ansatz, and then you find this coefficients of this ansatz, so that like variational using some kind of optimization technique, so that the final ground state energy remains minimum or the ground state probability is maximum, and so on.
So is there like a theorem that says that you can do it for a certain class of Hamiltonians, this process, or is it just like they tried a bunch of Hamiltonians and it worked?
the variational principle is true as long as you can guess better. So that is not general principle.
I see.
Yeah, I think it depends on. I think it.
So if this is also answer, this is also answer, both will give different answers. And one cannot relate the one to the other.
So these are all heuristic techniques that you try to see if you can do better.
Is that correct?
Yes, exactly. And I think it depends on changes from problem to problem as well.
Thank you.
Yeah. So this is the problem Hamiltonian that is usually used in as a toy problem in quantum annealing for the ferromagnetic T-spin model. It has a form of like this, like there are like p terms in expansion. And the nice thing about this model is that at the when p is greater than 3, it shows a first order phase transition where the energy gap closes exponentially with the system size. So this, for example, in traveling salesman problem Ising models, the energy gap closes exponentially in the for a very large system. So it's difficult to experiment like simulate like 50, 100 spins. In this, what can happen is for a very small system, you can see this very small energy gaps and you can test different techniques of quantum annealing. And
So both of them are exponential, just that one of them has like a better coefficient or something. Exponential, like you're saying that the gap closes exponentially in the system size.
yeah,
You said it happens for this ferromagnetic model and it also happens for the traveling salesman.
yes, but for traveling salesman problem, I think that happens in the like in a very large system after you cross probability.
So the coefficient of the exponential are different. For one, it's taking longer to get.
Not coefficients like the number of cities, for example. Have
No, I understand. Okay.
Yeah.
I answer what is good. It's just a matter of time.
But you see, this Hamiltonian should have a large gap. It's the total Hamiltonian that is an exponential.
Yes, in the dynamics, it encounters a very small gap in the quantum annealing dynamics. And another thing is that it commutes with this parity or S square operator. So you can write this system in this maximum spin subspace, eigenspace, so that for all simulation purpose, the Hilbert space grows as n+1, not 2 to the power of n. So it's easy to do experimentation.
This is symmetric subspace.
Yes, exactly.
But that will happen with any HP which is diagonal in sigma z.
Yeah.
If you start with any initial Hamiltonian which is sigma is local. I think for any you can find that.
Yes. Yeah.
Basically, you're putting all the degenerate states in one level and basically go to a rotated basis. Yeah.
Yeah.
You see only those states matter in the
Mhm.
Okay, and I have a very dumb question because I forgot my physics. It's been a while. So first order and second order phase transition, is there like a easy way of describing them?
So, so in this phase transition, in the sense, it's going from in the beginning, it is in a paramagnetic state, and in the final, the system, the ground state is ferromagnetic. That is the phase transition that is happening. second, I think it's related to second order, first order is this free energy. If it is
Yeah,
continuous,
because first derivative is discontinuous, then it's first order, second derivative is discontinuous, then second.
Yes.
But I don't know what free energy here because there's no temperature.
Yeah, so what does it mean?
No, but there is some temperature.
Magnetization.
In annealing, there is some temperature, right?
Here, I
Or
think
here.
this, I think here this is magnetization phase transition.
Ah,
No, but still I cannot apply thermodynamics without having temperature. So magnetization is ferromagnet, paramagnet, they all have temperature in them. It's standard statistical model, they all have it. So here missing thing is what is the initial step? If it is a thermal step, then there is a temperature also.
Oh, right, I see. So you don't Hamilton, you start with the, when they start with the curve.
but I think, are you talking about quantum phase transition? Or classical phase transition?
Definitions are same for both.
No, but quantum phase transitions can happen at zero temperature. You don't need to have any temperature.
No, temperature equilibration is there and zero temperature is fine for me.
But if you take a transversely rising model and you take just chain magnetization, right? You change the coupling and you
Yeah, I
change
think this happens in zero temperature.
This happens at zero.
Yeah, but I'm fine. As long as you apply statement, it's okay. You will get a normal. I mean, of course, at the time, you not get in 1 day, but that's how.
Okay, I'll bother you later. So sorry for the animation.
Yeah, so this is the toy problem, ferromagnetic free spin model. Here, so which means now the initial Hamiltonian, I call it Hx, which is basically like sigma, summation of sigma x terms. The ground state is superposition of all possible states. And Hz here is now the ferromagnetic free spin model. Now we want to find this an optimal driving like a counter diabetic term. And now we are considering a standard like a simple annealing schedule, which is 1 minus s, and this will be s in 1 minus s, so it's 0 at the initial and final point. And the answers we consider is this simple summation of this spin operators. So I want to find this.
I have a very down question. Shouldn't the SS sum to 1? Like, shouldn't the coefficient sum to 2? That's not.
I think it is.
Hamiltonian, also. Yeah, Hamiltonian, that's it. Not
Yeah, they don't have to be normalized. I was just curious about.
I mean,
Where sigma squares are.
S means smallest. Annealing term, yes.
I thought it was like 1 minus n s because at s equal to it's fine. No, that is 0 and 1 is both 0.
Yeah.
Sorry. Stupid question.
Yeah, so this is the problem Hamiltonian. So this is the we want to find this gamma I of this answered terms here, so that at the final time my ground state probability is minimum. So how we do this is
Okay, no, actually, sorry. I think I still have a little bit of a. Okay, I'll just say it again and we'll see how stupid I am. Because so basically you don't want to add a Hamiltonian which has a lot of energy, right? Because then you start cheating, because then you can go really fast. So you do want H to be normalized in some sense, right? Like, yes, whatever it is, it should stay constant.
Yeah.
But here that it looks like the normalization changes as you change S. Right? Because like suppose HX and HZ have the same normalization and the last term is not there, right? Then the normalization is at most both.
So, if I am understanding correctly, the thing was depending on the difference between I and N, right? Inverse of difference in I and N. If you add some proportional term, then difference can only change by some proportional, I mean, the term, s into 1 minus 1.
Are you trying to contest that you don't need Hamiltonian to be normalized?
No.
No, there will be some norm there, inverse norm there. Total inverse norm should be there somewhere.
If you look at the adiabatic time, the norm factor comes in.
We explicitly write it down.
Yeah. So this is what I mean by So it doesn't matter.
Okay, sorry for this stupid.
no problem. So this is the term that we want to minimize, the final ground state probability. Or we can also find the minimum energy. We can minimize the energy of the final state because in general, because we don't know the final ground state to find the probability this inner product.
So how do you check that? So so final Hamiltonian, if I don't know the ground state, then I cannot check that whether I found ground state.
We experimented. We have also done an experiment with final ground state energy. Final energy of the system, which should be minimum. You can measure the energy of the system.
I can measure the person.
If I give you an eigenstate, it's easy to check what its eigenvalue is.
Yeah, if you give, but that is the problem, right? You want to prepare an eigenstate.
Yeah, so if you know, for instance, that your minimum energy is 0, let's say, you prepare this state and you just check if the energy is close to 0 or not.
So at least you have something.
This verifier.
Yeah, so this means at least you will be able to measure the spectrum of the Hamilton.
Yeah, which is fine.
If not eigenstates, yeah.
Of the final Hamilton.
Final.
You're able to measure this being the maximum, right? Probability of the ground state.
Yeah.
Yeah.
Probability should be maximum. If we define it as the energy should be minimum. Yes.
And then again, it will depend on your answers. So you will not be able to reach to the ground state energy. So, I mean,
No, but this
this can only have some limit, right?
no, but this answer has enormous flexibility because you keep changing the chromosome to ensure that the fitness function has reached the maximum value.
It is just a scaling factor. It's not even very non-trivial. It is just sum of spin terms scaled by something, and you are changing the scaling parameter.
Yeah, actually, yeah, because if we optimize these coefficients, we saw that using genetic algorithms, this is sufficient for this problem to see the.
Exactly, the sufficiency is the question. That why it was sufficient, and I mean, how do you know that it will be sufficient? We are good at interaction here, right? This is the Smoker Hamiltonian that you are arguing. It's same.
Yeah.
Yes, there are numerics, right?
Yeah, exactly. So
Yeah, you can we also tried adding like S1, S2 kind of terms too. But even this simple was enough for this problem.
You can put mass the actual round.
Yeah, exactly.
you see, to find the optimal parameters here is like for a generic system is as hard as the original problem. So you can only do this for a
No, that I'm not sure because here I can write very simple. So for example, I can add identity here and try to find the coefficient.
but to find the optimal Hamiltonian, optimal coefficients that would basically
Optimal coefficients for identity extra Hamiltonian I may be able to find. If I had non-trivial Hamiltonian and then try to find the coefficient, then try to get it. I can always scale any Hamiltonian with identity. I can tell you what will be the ground state and what will be the ground state.
You probably have some examples, right?
Yes.
Where you have convergence for the genetic
Yeah.
algorithm.
Yeah.
And yeah, so just to ask, so what is the genetic algorithm here? So why is it work?
Yeah, so this terms this gamma we are going to we were finding this optimal coefficients using genetic algorithms. So this is like a heuristic optimization technique. So which is like for example, you want to find the minimum like this like the summation of three numbers should be 0, and then you start with the random solutions in the beginning. And then you evaluate the quality of the solution called fitness evaluation, which is like our ground state probability or energy here. And you based on them, you do the parent selection, and you see the best solution among them, and you do crossover, which is like exchanging some numbers between them, and then mutation you change slightly. So this is like inspired from this evolution. So in the end, after these several circles, the best solution will survive.
Yeah, so this is just like new names at this level because you need to define what is fitness function. You need to define whatever system you are talking about will have these things because mutation will not always be there. And you don't know which, I mean, you want to look at long-term fitness.
I think the mutation will
This
not
is
be
something we act.
That depends on evolution, right?
No, it's got nothing to do with the actual evolution. You're optimizing the
Yeah,
That is what I'm also trying to say. That this has nothing to do with evolution, just word, right?
yeah, it's
Yeah,
like
it's just
inspired from.
you're just optimizing using something.
Exactly. Then you can call it fitness, or I can call it energy, I can call it something else.
Yeah.
There should be more.
No, there are random changes in the. See, you have a string of bits, right? And so the gamma ones are used as bits. So if you randomly change one of the bits, that's the linkage.
Yeah, but I mean, so this is the thing that I don't know if in evolution, this is a good strategy or not, or at what time scales and what systems we are talking. So you are taking one strategy. Yeah.
Oh, well, but this is fine. It's okay. It's kind of inspired by that, but it's not identical.
and this is known like standard way of
We will talk
We're running a little short on time as well.
Yeah, so we start with this initial random generated solutions. For example, if there are three terms gamma 1, gamma 2, and gamma 3, and then we want to optimize it. And the fitness evaluation is that we evolve this whole do this whole quantum annealing dynamics, and we find the ground state probability, and then we do this kind of thing. So there is a lot of times we are doing this quantum annealing simulations through this process. So these are the results. So for the we are considering like n equals to 15 spin systems, and the adiabatic time scale according to that the time scale I shown, the it should be like 30, the adiabatic time scale. But I am here evolving until 3. So in the dimensionless, so we are well within the adiabatic time scale. So without this blue dynamics shows the evolution without any this optimal driving. So it goes to the probability goes to 0 at the final time, and because of the and with the solutions, the candidate solutions that we get from this genetic algorithms. So there are many of them, because if you start with different solutions, there will be different in the end. So all of them are like going to almost 1. So which is a good thing. So with this optimally driven Hamiltonian, we were able to get good probability distribution within a short time. And I tried for it's not displayed well until 45 spins as well, and the ground state probability was consistently higher. And
What is on the y-axis in that graph? Number of spins. What is on the y-axis?
this is a ground state probability.
Okay.
Yeah, at the final time of the annealing with the candidate solutions that we get from the genetic algorithms.
As you increase the number of spins, the probability that you're getting to the ground state is dropping.
without optimal driving.
This is without optimal driving.
That's what
It's
no
like,
way.
yeah, it's 0 to begin with, and it's like 10, yeah, almost 0. So with the optimal driving,
Oh, that's the dash line.
yeah, that then, and here there are boxes. I don't know why it's not displayed well. So it was give consistently good results even for large systems.
So I have a very dumb question. So if you the amount of compute that you need to derive the optimal parameters, is that comparable to the amount of effort
Yeah,
you need
it's,
to analyze? Or
Yeah, it's a very expensive process actually. For problem to problem, you have to find this and yeah, take
but
up.
is it this? It's a very dumb question. Does it happen to be cheaper at least than diagonalizing the full patient? Do we know?
Then I
It's
don't
not no.
not-
My conjecture, and
No cannot be an answer. Otherwise, I will do it.
it isn't.
No.
Like we don't know of any sort of scaling, generic scaling for any of these heuristic methods, which they will tell you that this is cheaper.
But at least in these
Small items, yeah.
I mean,
I did not understand how the genetic algorithm, when you use that, how you're using quantum information. That seems to be, I mean, the way you have used it, that would be for the usual quantum problems. I do not see where the quantum.
Not quantum, it does, but quantum.
there is
No,
no quantum
I mean,
any
there's no
quantum
quantum effect.
no in genetic algorithms.
No, that's. They're not using the quantum version of the genetic.
Yeah, it's like
algorithm. They're just
using
using
classical algorithms to help
yeah,
quantum annealing.
So maybe it might help Lalpuda if you go back to the genetic algorithms slide. So these things, right? Parent selection, mutation, crossover. Let's say take this problem that you've taken, this ferromagnetic spin model. What were your parents? What were the crossovers? What were the mutations?
Mhm.
Like if I want to create this OD, like optimal driving Hamiltonian,
Mhm.
how would you go about setting these things so that you get to the best solution?
So that would be randomly that, I mean, that's there in the
Yeah, there is-
But Malandra, he is asking which one is best. So gamma is mutation or gamma is crossover or gamma is quantum.
So gamma 1, gamma 2, gamma 3, the whole string. The crossover will be like from one chromosome to another chromosome, we break half of it, mix it with that.
Hello, but what is chromosome in this language?
Sequence of balance. And what is it? What is it that you're optimizing at the end?
So the fitness function.
Yeah, that is also
You
arbitrary.
keep throwing away combinations which do not give you optimal value of the fitness function. You keep choosing only those which give you lower value, the lower or higher.
And the fitness function here then should be informed by the problem we are
Okay.
I don't see that it is the quantum evolution here. I mean, quantum in the sense of, not a classical quantum.
So this fitness function, if we execute on a machine, or do you?
Yeah, fitness function. Yeah, in principle, this happens on a quantum annealer kind of. So
So whether or not it succeeds,
yeah, we simulate, like we do the numerical simulation. So fitness evaluation is when you perform this quantum annealing of the whole thing with the solutions that we have in hand.
you're checking how well they perform.
Oh yes, exactly.
Oh, so you run the annealer, you take your initial guess of the OD,
Yes.
run the annealer, see what you
So,
get.
Yes.
so every time you are doing quantum annealing also, while you are
Exactly.
Okay,
Exactly.
that helps.
Yes.
Yeah.
To understand.
Thanks. Thank you.
So it's like your variational algorithm, except the variational circuits are now your annealer.
Yeah.
Yes, exactly. So that was about finding an optimal driving operator and then maximizing the ground state probability.
Nicola and
Yeah.
And so there is, we can also just engineer these annealing schedules, like tune these rates at which we modify the interactions, and then see the improvements as well. So, for example, in the most test and simple cases, this 1 minus S and S, they are not really the efficient ones for real problems. For example, this was from a couple of years ago. This D-wave annealer uses S and A of S and B of S, which looks like this. They are not linear. And for example, there is a paper by Roland and Self, which where they for Grover search algorithm, they find the optimal annealing schedules by implementing what something called local adiabaticity, which means you implement adiabaticity at every point of quantum annealing, and they were able to obtain this quadratic speedup in finding the ground state.
what you're putting by implementing local adiabaticity at every point in the evolution.
I will come to it actually later. So the main message is that you have to engineer this A of S and B of S for different problems to get the maximum like higher ground state probability.
So what this means is that, okay, if you choose S to be T over T, so if your schedule is linear, you don't care about regions where the gaps are higher or lower, right? So what you do when you do a local adiabatic schedule is whenever the gaps are higher, you can go faster and go faster.
Yes.
So
Yeah.
DSDT then matters, right? Here DSDT is like uniform. There you can engineer it, make it linear.
So basically, yes, depending on a function of the
Right. It's a
different from T. That's what is that what you mean by local adiabaticity?
Yes, exactly. So similarly, we used genetic algorithms to find this annealing schedules as well. We start from a polynomial ansatz, and then we find the coefficients of these ansatz to see if we can optimize these annealing schedules. So here now the chromosome for optimization are these alphas and beta terms for both A and B. And of course, they follow this boundary conditions that A will be maximum in the beginning and B will be maximum in the end. And again, the fitness function is this ground state probability. And we were able to see for smaller spin systems, for example, the ground state probability is higher at the final evolution than compared to the linear schedule, a simple one. And these are the annealing schedules which are gotten from the genetic algorithms. But at the final for like large spin systems, this method was not so efficient. It almost goes to a smaller value, but I don't know if it is comparable still without any engineering schedules. reaches even much lower values.
So that's nice. So it's a combination of both the schedule and geometric.
This is
Graph and
just
stuff. Just the schedule.
just the schedule.
Okay.
So with just the schedule, we were able to get good ground state probability in the end, but for smaller systems. So this was all using genetic algorithms because, like I said, for every problem you have to run this annealing multiple times during the optimization.
So I have a dumb question. So if you go back to the previous slide, how do you change the schedule? This is also done by calculation.
Yes,
These
so
are the genetic algorithms.
yes,
Okay.
here this A and S have this scheduled
To
consent.
give you an idea as to how difficult this is. So let's take the most simple case. Let's say HS is just a one-dimensional projector, like they do in Grover, and HZ is your any sigma z diagonal Hamilton.
Okay.
Then you can show analytically that there's only one, so there's only one point where there's an avoided crossing. But it's not. So if you want to predict where the avoided crossing is, because that's what you would need to do a local section. So predicting that point exactly is sharp pillar. Approximating that to the end pillar, which is the problem you are trying to solve.
That's the type of there.
Yeah. So these are very difficult things.
Yeah, so this is
Can I ask why the genetic algorithm? Why not some? So there's like many algorithms. Why would you want to try other classical algorithms?
Yeah. I think we tried some gradient based methods. The solutions was not good.
So
Genetic algorithms were surprisingly giving good answers. Yeah. So yeah, so because we want to find the schedules each for each problem, for example, in ferromagnetic field model, it's a very not so practically implementable way. So we thought of maybe we can train a neural network to teach it the annealing schedules for some systems and see if it can predict for a new system. So to train this system, we used this local adiabaticity condition, which Shantanu was explaining earlier too. So instead of so at every instant of time, we say these terms which are like the cross transition terms and divided by the energy gaps. They should be less than a certain value epsilon. And if we just parameterize this, it goes to this ds by dt being less than this. And then considering a maximum case, we arrive at this solution like a functional form for the annealing schedule T of S, which has this form, and we can invert it to get S of T. So, so it basically like what this local adiabaticity condition shows is again like whenever there is energy gap is very less, you drive it slowly there, and whenever there is a large, you can drive fastly. And this gives us the functional form of what S of T can be. We can compute it this schedule.
It does not. It's not to compute precisely because again you have differences in energy.
Yes.
Like values.
Yeah, so it is difficult. So for the training set, you put effort in creating,
Okay.
and then
Like a one-time cost.
yeah, hopefully then it predicts better for the. It was just a trial because also for and then here we try this max cut problem kind of solution like problem which is like the Hamiltonian of this form which has two equal fractions, and then we for this Hamiltonian for different instances of Jij and Hi, we create the training data set and find the local adiabaticity like the optimal schedule using that technique.
What cycles are you looking at here? How many keywords?
So this is a small system because it's difficult to find. Yeah. So like five spin system. It's again a toy problem. So we create for like the training data set for a large number of data set, and we train this. We use this LSTM neural networks, which is used to find this time series prediction. This kind of
What does it stand for in this case? Is it important?
long short-term memory neural networks.
Function.
Yeah, yeah, it's a recurrent neural network apparently, and then there are some modification in this recurrent neural network to avoid this gradient vanishing problems. So it is more trainable than the standard recurrent neural network.
What is it occur? Is it too hard to explain?
Yeah, for me, I just treated them like a black box. So they are like in addition to this, there is like kind of interconnection between these nodes as well. I think.
So why these? Like when you have to choose, why did you pick these as
So-
things?
So there was another paper where they used LSTM for a similar task of finding minimum energy gaps, which is this is basically just one step later. So we use the same network just to try and and then just we compute the schedules at discrete times, at points, and then we use it to train the neural network with this mean squared error kind of loss function. So this is the
What's the MRE?
mean squared error, mean relative error. Yeah, because they go from 0 to 1. Yeah. So this is like the training results, and so this is like for a number of test cases. We like here we have used like n for n equals to 5 is the training data set, and n equals to 5 is the test data set. That kind of. But we see that the error is lower, but with increase in the number of spins, it's not able to predict well. And this is how this is how examples like this is the schedule which is supposed to be according by using local adiabaticity condition, and the ones predicted by the deep neural network, the LSTM neural networks. And if we look at the annealing schedules themselves, so it closely follows the local adiabatic schedule in terms of all of them. But then because it's a small system, the ground state probability is not so bad to begin with. It's almost 0.9 already. But there is some improvement using this local adiabaticity or the optimal schedules, and also deep learned, the predicted one follows the path very similarly. So we tried some other experiments, like we consider this kind of a graphs, which is because the Hamiltonian we have is like a Maxwell problem. And then we train using this kind of data set where there are like 3 edges, and we ask it to predict for like all edges. And similarly, we for all dual connections, we consider like triangles and quadrilaterals to generate training data, and then we ask it to predict for the problem where they are all connected. Yes, exactly.
Train on that.
Yes, exactly. The
What is
errors.
large N? When you say large N, sorry to interrupt. You said predictive results is at large N. What is large N? Roughly?
Yeah, the number of spins in the
No, what's the number? Like you said 5 in the previous
Yeah.
one. Now it's abstract or
here also it's 5, and I trained using, for example, the training data set has only like 4.
I see.
Yeah.
Makes sense. Okay.
And it does well generalizing to a larger system, but still it's not as good as what it would do for a smaller system like it was trained on. Yeah, these are just to get a glimpse of how deep learning can be used to train this kind of things to annealing schedules and so on. Yeah, I think this is the end of the first part, the story of quantum annealing. And then now I will move to this second part.
Yeah, about 25 minutes.
Yeah, this is the Yeah.
We also asked a lot of questions.
Only for discipline.
Please go ahead and ask. It's more interesting to have. Yeah, so this is the work that I did at KDH. My funding was from this plasma peptide seq. These are Euro HPC projects to where they aim at making the plasma and fluid cores exascale ready. by doing software engineering and so on. And there was small task of exploring how computing can be used in plasma and fluid dynamic simulation. So this was an effort to connect to that project.
So when you say exascale, oh my god, we don't have time.
Yeah, they're just basically big supercomputers which are bigger than what they had until now. So they have to change their codes to make it ready for this bigger exascale computers. So here I focused on plasma simulations. The plasma simulation is a very important topic. It's used in many different kinds of areas like fusion, accelerated physics, understanding space weather, and so on. And particle in cell is one of the methods. It's the kinetic simulation of plasma kind of a method. It's a computational method basically to simulate plasma, which is basically like charged particles. So there is another simulation method called magnetohydrodynamics where people treat plasma as like fluid but with charge. So that is another way, but this is more you don't treat them as fluid, just as particles. So and generally for real problems they require like huge computational resources and so on. And for example, this is one of the from the project I've worked on. It's from a code called big on GPU, which is particle in cell on GPU. It's code run on GPUs. It's for the accelerated physics. This is like the simulation, how it looks like it, all the simulation, all the fancy usually in the talks and so on. Yeah, so this particle in cell simulation is this way method for there are many charged particles and they are mapped on this computational grid kind of like a mapping, and then the electric field on this grid is interpolated.
So what is the grid representing? Is it physical space or?
No, it's it's a computationally they approximate everything on these grid points.
If I'm not okay, so what is the relation with plasma? Like every point represents.
So every point here represents like charged particle, like electrons.
Okay.
Yeah, and
So they cannot go outside the grid. Like everything has to stay in the cell. Like every.
no, I think they move when they move, they change the approximation of these grid points. When
These are relativistic particles as well.
I don't think for in this example I haven't considered this relativity.
Okay, so you were answering the-
I think all kinds of like they can be electrostatic and sometimes you go to electromagnetic and so solve the full Maxwell's equation and so on.
Yes, I have a very simple question. So this grid versus not having a grid, what is the difference? Because like it seems like at least in the picture you're storing the full location.
Yeah.
So what is the difference? I'm not.
So it's just a mathematical approximation. I think they allocate memory on the computer at these grid points and this kind of.
I mean, it's the same, right? You want to solve any
Discretize it, if you discretize it.
Yeah, this is the thing.
Yeah,
So what is its
I don't
relation
know
to
because
plasma?
each grid point represents like 200 particles. It's like
And this is like plasma of 200 particles.
yeah, exactly. So if there are like 10,000 particles, you consider 200 grid points. So you simplify all your calculations to these
Then you can
200.
work out the density.
Yeah, exactly. So and when they move, you find the force. They kind of induce this electromagnetic field or electric field, and they because of which they are like self-induced field. They move to it, and you find the force on these particles, and they are moved. And after each movement, there is like a charge density changes again, and then you solve this Poisson equation. And then electric field is formed from this gradient of this electric potential to find the new electric field, and this cycle goes on for several steps. So you see what happens and at different times, but you see how the plasma changes with time. So what I try to do is offload this whole Poisson solver to a hybrid neural network which has both classical and quantum parts.
So how plasma changes, you mean you will compute the time evolution of the density of this?
Yeah. So in this whole cycle, so after the density is updated, to get the electric field, I use the instead of solving it on the computer, like using like discretization and linear solver processors. I try to use this a trained neural network which does it for me.
So to answer your question, you start with the grid of densities, and then you run this, and you get the next grid of densities at the next step, and so on. And how she does it is, if I understand well, you're going to require a different.
So in case of plasma dynamics, we usually treat it in two ways. One is the fluid, classical fluid theory, and again in statistical mechanics, we use two ways to solve plasma dynamics. Now, in this case, what you have used, whether it is fluid or the statistical approach.
So this is not fluid approximation. It's, I don't know. It's like you see. I think it's like you see each particle what it is doing, kind of a simulation.
The end result is the stable configuration of the 100,000 particles. What is the end result?
So in the, I think it depends on the problem. In the toy problem I have considered later, it should reach kind of the electric field will increase exponentially in the beginning, and then it kind of saturates.
Stable.
Yeah. Yes.
So this is device theory actually. Means you put in a charged particle. Means suppose you have a positive particle and you put a negative charge in it. It gets shielded.
Yeah.
Yeah.
It depends like on the problem. There are problems like Landau damping. You start with some configuration and their electric field damps. So it depends on the initial condition on and which charged particles are used.
Also, the charge particles, they don't change their charges themselves. So these are like elementary kind of things.
Yeah, no, they only the charge density changes on this grid.
So if I have 10,000 points, they are like elementary particles with the given charge. They will remain in this. They will change their position.
But you don't look at it at that level. Yeah, you look at their densities.
Yeah,
Okay.
also the total energy is conserved. Total momentum should be conserved.
It's an isolated system. Right?
Yeah,
That's
yes.
not driving.
And it's a classical system at this level.
Yeah, it's a classical system. It's everything is classical. Just the quantum part is that in this neural network, if I add a quantum circuit in this neural network, if it does better job than just using classical network, or if no, for all purposes, the ground truth is the normal finite element methods that are standard used in a standard way. So yeah, that the aim is to reach as good results as them.
Like here, the particle will be in motion, right? Because you are solving this Newton's equation, X and B both are given. Then why are you taking this electrostatic equation? Like, for example, only there is no magnetic field, right?
I'm considering only electrostatic in this
If
problem.
the charges are in motion, then they will be magnetic.
Yeah, but this is like the approximation model. This is like electrostatic. There is also electromagnetic, which is yes, better approximation.
Because like the static electricity case, like, the configurations are like really highly unstable. Like there is Armstrong's theorem. It says like no static configuration of charge can remain in stable configuration. So either like everything will collapse or like divert, or like by the use of this electromagnetic field like coupling, then they can come to a like, stable configuration.
Does it also apply in case of plasma? We have a criteria to become a plasma. You have to satisfy criteria called divide length. That divide length is necessary to satisfy to form this whole state.
And what is that length correspond to? What is this length?
It's
The characteristic length of charge falling down from a central particle, and we go away from a central particle, how the charge usually exponentially falls.
so that the whole thing doesn't collapse.
No, the thing is, and does that restrict the magnetic field? Because charges are moving, so they will create magnetic field.
No, as Shastri was saying, actually, it's the local density that actually, not the particles. There will be motion, there will be fluctuations, but the local density is stable.
No, I was saying that what if there is a magnetic field there because of the charge?
There is no magnetic field.
It's just the Poisson equation that she's solving, and she's looking for a stable density. The particles may still may be in motion, but the average density will stabilize.
or instantly. So if I understand correctly, so this where the Newton's equation is coming. Because like for example, let's say I have this Poisson equation, then I can like solve that by using some techniques. It's a like static configuration, I can like solve it. But then when we are incorporating the Newton's equation, then the particles are in motion.
Are you using Newton's equation at all?
Yeah, I'm using here, but in principle, yes, in a realistic scenario, we have to solve full. There is also magnetic term here in the Newton's equation, and also here in the in addition to finding the electric field, we also have to find magnetic field, effective magnetic field after everything happens.
Yeah, then we need to use all the
Yeah, yes, exactly. This is the kind of a toy problem, and with just using electric field also, you can see this Landau damping phenomenon and this two stream on instability problem, which is the one I'm
So I guess the force is being used only to update the position.
upgrade, yes, to move the particle.
And once you update
Yes.
it, the density keeps changing, and you look for the stable density after.
Yes.
whatever.
that is your linear systems in a way, right? That is
Uh-huh.
the density at the next step.
Yes. Yeah, it's just moving the particle, pushing the particles to next step at every time. So we look more into this part here. So this is my neural network. It has in one first layer of classical, the one I'm considering, and it is followed by this quantum circuits. Here, what I give input is like the charge density at different grid points. Like I have like 64 grid points in my problem, and I give the charge density. And after the first layer, there is like AX plus B kind of transformation here, and the resulting is fed into the quantum circuits. There are different ways of feeding this data to quantum circuits by preparing the system in different ways. Here, what I'm using is amplitude encoding. So I'm for 64 numbers, I use 8 qubits, and it is prepared in it is encoded in the amplitudes of this quantum state. So and then that is followed by these trainable ansatz, which is this rotation gates and some control dot gates, and there are multiple layers of such which we need to optimize. And in the quantum output, I'm considering.
One thing this is a particular model of quantum neural network, right?
Yes.
Because it has been also more evolved with the JJ gates and other different type of gates combining two inputs together. So it means people have evolved this quantum neural network with more complicated gate structures. So I think this is the initial one, that quantum neural network, which has the rotational.
Yeah, I just use the simple one to make this experiment. Yeah, there are many different kinds of
variations.
Yeah, there are many different kinds of answers.
When you use correlations in this space, there are people say that there are more you get better results on
Yes. So that is like created by this entangling gates.
entangling gates.
Yes. And then the quantum output I consider is the probabilities of each when measured in the computational basis. There are 64 numbers again, and that is fed to the final classical layer, and there are the usual activation functions which are associated with classical neural networks, and this final should be the my electric potential, which
What is the activation function for taking to add it to the output?
Yeah, that is like
summing them or something.
So for every number that it has, it's getting from here that tan h function something looks like this. So for given x, what will be the tan h function?
And then you can understand all the data that the output.
So it's in a way aggregating it to
Yeah.
like the high or the lows.
Yes, exactly.
Main purpose they use it just to add non-linearity in the
Exactly.
everything is
Exactly.
linear.
Exactly.
Thanks.
And in the quantum circuit, the only nonlinearity comes if we were to use just the quantum circuit, no classical part. The non-linearity comes only from this measurement process. The rest of them are linear operations.
As per the understanding, so you have a classical problem at hand.
Yes.
You are encoding in quantum state,
Yes.
and all benefit that you can get, whatever is available in quantum computers. So, whenever we only have covert search and source algorithm that is giving you benefit, and like few other algorithms are there.
Mhm.
Other than that, you cannot prove anything else, right?
Why?
Yeah. And so this quantum machine learning, so there are
Because you are using what? Okay, so the question should be that what kind of algorithm you are using? Is it related to those
It's a-
algorithms or
it's variational algorithm.
the variable?
Yeah.
Yeah, so these alpha, beta, gammas are things that you tune based on what you receive at the output. This is like
So-
multi-step.
Yeah, and there is no guarantee that it will give a good.
And what was the like your what is the word? So what function you are optimizing in this algorithm function?
Yeah. So
No, what is this function?
yeah, I will. So for this case, for example, if I'm giving the input charge density and output this potential, whatever it is predicting, it should match with the correct potential. It's like a mean squared error between the predicted one and the correct potential.
What was the correct potential?
You compute it numerically.
Yeah, so numerically, I use the finite element method to create all these cycles. The whole cycle I compute with the traditional method, and I know for what charge density, what was the electric potential. I generate the
This
data.
is the difficult part.
Yeah,
Okay, so you have a very expensive classical algorithm. Tell me if I'm right.
Yes.
You have a difficult classical algorithm
And that is
whose outputs you're using to train the network, so that then you can run it on bigger instances without running the expensive classical algorithm.
yeah. So only this part. So rho is the input and phi is the output. And I have generated for what rho should be, what should be the phi. For like for example, 1,000 steps of this.
Yeah, and if you change anything, then you don't know that the solution will scale, is it?
You don't know, right?
You don't know. So this is the whole thing with
Then when you are using a bigger system, then what is the
There's no guarantee. Just hope it will. I don't know.
Yeah.
Is there a unique file for every row?
Yes.
A unique file for every row.
I think so. Yes.
that I will know because there is
Like
standard
it's
statistics, right? So you are given a charge density and computing potential. I mean, there is great freedom at least. I think.
Yeah, that's what I was thinking.
So I will not say anything. I don't know.
But because, but then it's not the reality. No, she's not taking any relativistic term. Maybe
Fair enough.
not relativistically you have a union. Yeah, okay.
I mean, boundary conditions are not there, so uniqueness is out of question at this level.
No, boundary conditions are there.
Yeah. Boundary conditions are.
this
You're
section
on
is
the great.
I want to read them.
Yeah. Yeah. There are boundary conditions. That's why there is unique solution.
Yeah, then there will be.
Yeah.
Is it like cyclic or is this hard boundaries? Like do you make it like a sphere or something?
Yeah. Yeah. It's like zero in the beginning and at the end, kind of like. Yeah, so this is our hybrid neural network that I'm considering. I make like experiments. What happens if I just use 3 classical layers and use quantum classical layers to see if quantum is bringing any advantage.
You have about 5 minutes. You want
She can proceed. She can proceed. Also, if you change the depth of the network here,
Hmm.
do you also study that how the result is changing with the change the depth?
Yeah, yeah. I didn't make very a lot of experiment with different number of depths. I chose one. I think I used 5 such layers or something because it's very expensive, very slow to run this algorithm on a classical computer. So yeah, and then another interesting part is one thing is to use this data to find the like to train the network. The other way is this physics informed network. So which is that for the whatever the prediction is happening, it should satisfy d phi square xit by dx square plus the input should be minimum because it is satisfying that Poisson equation that we know, that is the physics informed part. And in addition, you can also give some hints such as if you have some data from experiment, the electric potential for a given charge density you can give. But in general, for many problems, for a simple Poisson equation, you can just use this training to get the solution to the equation. So that's one of the nice things using.
ND is much larger than NG. I think.
Uh, yeah. And for example, in this method, I have given a lot more NG and less ND to see if physics informed does has a better contribution. Uh,
But these are also choices, right? So there's no way that I can say that energy has to be larger or smaller than GP.
yeah, NG you can set any number of points because it's just yeah.
Yeah, I'm just saying that this is LSR, that you can use this thing as well.
Yeah. Yes, exactly. So, so in principle, if you don't have, you can do it for continuous system as well. Like if you don't have data set, and you can also differentiate or find the gradients of these quantum circuits. By if you have, for example, if you find a quantum circuit which approximates phi of x, you can find the with the same weights you can with using something called parameter shift rule you can find d phi by dt as well. So in general, you don't need the discrete points. You can continuously find the gradients and the function approximation to define this physics informed method. So this is the toy problem that I have considered two strain instability problem, which is like there were like initially two lines of electrons, and because of the self-inducing electric field, they interact, and this is like the characteristic. There's like a void formed. These particles form, and the total energy should be conserved. This potential energy or the electric field amplitude, which is related to that, will increase and settle at some point when the void is formed. And this is like the total momentum will be conserved. This function should be symmetric uh, at all times. That is the ideal case. And this is how the electric field varies in different points. So this is my solution with using traditional, just classical and CQC. They seem to do the job like this, creating the void, which is the final thing. And if we look closely, this is the final particle distribution in the phase space. If you were to look more closely, the velocity distribution, this is velocity x. So this is traditional, it should be symmetric. CQC seems to have more symmetric distribution or more closer to the traditional one than the using just the classical neural network. And to see how the total energy is varying, it should be conserved ideally. But both classical and this hybrid network, they are not. They are like if you look at the scale, it's varying at a small scale. But it seems like CQC is doing slightly better than the other. But this is one of the drawback in the simulation. And when it comes to electric field growth, both of CCC and CQC are predicting the good electric field amplitude. And this is how this is just to give an idea of how the electric fields look like for at different time steps. They are like very different from each other. So and for these simulations, what I have done is I have started trained with different velocities like like electronic beams, and I have predicted for a new test case. This is the result of that. So they are quite different from each other, not very easy to generalize to a new system. And CQC, this is like general steps, but I have seen that most of the time CQC does similar to the original, while this red CCC is slightly deviating. And that is also shown in this error for 1,000 time steps for this test case. And when it comes to the number of trainable parameters in the whole network, so for a similar number of trainable parameters, the quad CQC does consistently better, while CCC not so. They are like similar, but CCC is consistently giving higher error than the quantum part. And this is the result using physics informed method. So suppose that if I don't have the data set which is dense, for example, I don't have the data in all 64 grid points and I have 20 grid points only. So for the dense case, this physics informed part is not doing much difference in both classical and quantum. but the prediction is the difference is drastic when it comes to the sparse data. For example, if you have only n put 20 data points, because of the physics informed approach, it's performing as similar to like we had all the data set. So that's the nice thing about this encoding differential equation in the training part. Yeah. Yeah, this is the conclusion slides. Like I talked about how classical quantum algorithms can synergize to give better results, and in the NIST quantum computers, this kind of problems is what we are continuously seeing. And then, like for fluid dynamics and particle method, we can use the hybrid or quantum methods, which is they are like one of the very hard problems to exist, and people are looking for computational resources, but it's not. The results I showed was very. It is good that it's giving better accuracy, but it's not really a proof that it can replace the traditional classical solver. It's a way to go, and yeah, physics informed neural networks is very interesting. Like without data, whenever there is less data, you can use the knowledge of differential equation and can do a lot of difference. Yeah, thank you.